Thanks, Adrian, and thanks everyone for being here to listen to this presentation. We've talked a lot about renewable electricity, but we've barely touched on renewable thermal energy. There's been a couple of cases shown during these last 2 days, one of which failed to make the economic mark and another one which did. And if it was easy, well, we wouldn't be up here talking about it. I'll quickly cover Alcoa's energy needs, greenhouse gas emissions and sustainability targets. Then I'll hand over to Bassam to talk about solar energy research for minerals processing, being led by the University of Adelaide with support from ARENA and many other organisations. Alcoa in Australia is vertically integrated from bauxite to aluminium. We need 7 tonnes of Darling Range bauxite to create 2 tonnes of alumina, which is smelted to create 1 tonne of aluminium. I'll be discussing the alumina refining process, otherwise known as the Bayer process, to make alumina from bauxite. Energy is critical to the process. A typical energy split is about 2/3 for energy for steam and electricity generation, and 1/3 for calcination, which is used to drive off the chemically bound moisture from the alumina. Alcoa has the world's largest integrated bauxite mining and alumina refining system here in Western Australia, with 3 alumina refineries within 150 kilometres of each other. 9 million tonnes of alumina is produced per annum. It's approximately 43% of Australia's total alumina production and approximately 8% of total world production. We use 25% of the state's domestic natural gas. We underwrote the Dampier to Bunbury natural gas pipeline construction early in the 1980s as a foundation customer. At our Pinjarra refinery, we partner with Alinta with efficient gas turbine waste heat recovery cogeneration power stations, which supply 15% of WA's electricity. At Kwinana, we have the Global Centre of Excellence dedicated to improving energy efficiency in alumina refining worldwide. At Alcoa, the business case for reducing greenhouse gas emissions is compelling. The business case is supported by cost. As we see, renewables are reducing in price, particularly for electricity, but baseload electricity is still a challenge. There is product differentiation. Customers are wanting to lower their greenhouse gas footprint. Alcoa has aluminium products certified to have less than 2.5 tonnes of CO2 equivalent emissions per tonne of metal, which is 75% better than industry. There are community expectations. To achieve our targets, our target is to reduce our energy intensity from a 2005 baseline by 15% by the time we get to 2030. 5% of our management variable compensation is based on achieving greenhouse gas targets. Our refining energy intensity has reduced by 8.3% over the last 10 years. This has been driven by improvements in operations, efficiencies, and also by expansion of our most efficient refineries. West Australian refineries are among the most efficient in the world. We have done well making incremental improvements. However, we need to step change to achieve our greenhouse gas targets. Renewables, and in particular concentrated solar thermal, provides an opportunity to achieve our targets. We are working in collaboration with the University of Adelaide and other parties to assess the economics of concentrated solar thermal in alumina refining process. I'll now hand over to Bassam to talk about the more interesting part of this presentation. Thank you. Not sure how it works. There we go, you're away.
Hello everyone, and thanks Ray. As the slide shows, this is an ARENA-funded project in collaboration with Alcoa, Hatch, the University of New South Wales, ITE Power and CSIRO. So we're looking at how we can integrate renewables into this process, and the reason we're doing that is quite evident on the screen. $5.3 billion per annum is what alumina brings to us, 160 petajoules per annum in terms of natural gas usage, and almost 40% of Australia's CO2 emission from, or part of the mineral processing component. So our approach is to integrate concentrated solar thermal into it, mostly because electrons and electricity will not cut it for this. And the objectives of this, or the drivers, are quite clear. Fuel saving, reduction of CO2, obviously fortifying against fluctuation in fuel prices. And we're hoping also we provide high value products or low carbon metals. So we set the objectives in 3 parts in collaboration with ARENA. We wanted to put a solar share of 29 to 45% in the bioprocess. We wanted to advance the commercial readiness of the technologies we're dealing with along the technology readiness level as we do. And also we wanted to put together a commercialization plan and provide to Alcoa some options for the future to use. So in doing this, we concentrated on Pinjarra, and we had 3 programs. The first one was looking at solar reforming solar steam. So this is for the digester. We had 2 options in there. One is just generating steam at 180 degrees, or to go for combined heat and power, where you use your high temperatures for electricity generation, and then what's left is for your process. The second part is the solar reforming, and that's taking natural gas and converting it into syngas, and that will add around 20% energy into it. And the third one is the calcination process, and that's where cavity receivers and high solar thermal concentration will get us the high temperature for the calcination to offset the use of natural gas. So in this we had the 4 different programs, and in the bottom you see the logos of the different people involved in it. We wanted at the start to also do techno-economic of the whole process, and also for the different components of it. So we wanted to identify viable technology paths. We want to compare it with alternative routes and options, and we want to benchmark also industry, local and external modeling of the process. And the other 3 programs is the low temperature that I mentioned before, and in there we wanted to evaluate integration, and we want to compare to all options. Solar reforming has been demonstrated by CSRO on an on-sun reformer. So here we were looking at how can we integrate it into the bioprocess, and also issue of storage of syngas was big in this program. And the third one is the calcination, and that's mostly done by University of Adelaide with the collaboration New South Wales Uni. And they're here, we're saying how we're going to achieve these high temperature for the calcination. In fact, a big portion of the energy consumption, and we're looking at different options there. So I'm going to go through each one of the program and give you a little bit of insight where we're up to. We did pass the first stage by ARENA, and the program is now ongoing. So for the program 1, and this is looking at the low temperature part for steam, we looked at process modeling, and we looked at 2 options. One is the parabolic trough or the central tower, and compared the economics for both of them and how it integrates into the bioprocess itself. So we had preliminary technical specifications and identified target design points for operation. And we evaluated the plausible sites where we actually can fit it, and we obtained real, albeit confidential data from vendors of what would it cost to build one of these systems. And we were pleased to see that we could achieve the CST percentage, which basically solar share. That means offsetting the use of natural gas in this case. And you could see there, depending on the where we are, obviously here the NDI is important, and the 4 different locations we looked at, and you could see the solar multiples of 2 with 4-hour storage gave us quite good options with sort of a useful NPV to look at. The second one was the tower system, and you could see here we could reach up to 54% of percentage of solar share with 7.3 hours of storage and 2 solar multiples in there, and with MPV in the positive territory. So the future work here is looking at the feasibility of CST. We have to issue a report by December 2019. We're going to look at the land and availability. We're going to look at configurations, short, mid, and long-term potential, and actual quotes of what would a system like this be, and cost, and where would be set in a way. The second one, which is looking at the solar reforming, as I said, the technology has been proven. So we looked at process modeling and integration into the bioprocess. Now, you've been using methane before, now you're going to be using syngas, so there's a little bit of changes of the fuel. The amount of air used is different a little bit, but these are all problems that we were able to find solutions for. And we want to find what's the most prospective opportunities for integration, and in this case, actually, also storage becomes an issue. So in doing this, some of you know about reforming, the ratio of hydrogen to CO differs depending on ratio of your methane to steam and other things, but we found that the 1-to-1 hydrogen to CO will give you the highest fuel savings per CO2 reduction, and reaching sort of closer to 23%. Further work here is more in the economic side and full feasibility and how it's been integrated into the process. The third one is the calcination. We did techno-economics as well on this, and we looked at 2 configurations, and we were trying to identify what the highest value and will give us the most reduction in CO2. So in those, we had the direct approach. This is a patented technology that we have developed. It is a hybrid system. So we call this a solar expanding vortex receiver. Basically, you're putting particles inside that is being circulated, where aerodynamically it's been built specifically for this. It can operate on solar only. It can operate on combustion only, or can operate on a hybrid mode. And it can sit on the ground where you have a beam down, or could sit in a tower when you have a beam up approach in a way. In looking at this, and we see with integration, I don't know if you could see this right, but you could see 2 inputs into the yellow, what's called furnace in there. You have a CST input. You could have hot air coming from the furnace, and then obviously the products coming in. So we integrated through this receiver I showed you before. In looking at this, we looked at 3 different places of interest, Pinjarra, Gladstone, and Learmonth. And we looked at what would happen in terms of solar multiples. And those who don't know, solar multiples is the size of the solar field above the the specified capacity. And again, we looked at fuel savings, and you could see that we can hit quite, north of the 20% mark, depending obviously again on the location and how much solar flux do you get in there. But also you could note that at some point the relative gains become small, so you don't have to say, for example, above 2 or 1.5, you're not really gaining much by increasing the size because the efficiency drops. The other one is what we call indirect in a way. So here now you're sitting a field which heating air, and this air is being fed directly into the calciner. And you could see the numbers here now looking much better, up to 50% and above solar share. And actually, we found the best optimal position is something like that, with around 16 hours of storage. And here you could see hot air at 1,000 degrees. So here we need to complete the development of the high temperature solar air heaters. We want to look further at how do we integrate it techno-economics, and develop further plans with and without solar reforming. I'm almost there, so more information can be found on our CET website, the Center for Energy Technology, that I'm the Deputy Director of. And finally, I'd like to invite you to this high temp forum. As Ray said, there's a lot of talk about replacing diesel, about generating electrons, but there's a good portion, as I showed you at the start, of energy spent in these high temperature processes. And we want to have this forum and open discussion. International speakers are coming in to try and answer some of these questions. We have a flyer on our booth. Please come and grab one. Thank you very much.